The day is finally over, and the demanding logic of the sun has faded into the quiet of the night. Settle in, and let the weight of the blanket anchor you to the mattress. You might feel solid right now, heavy and unmoving, but that is just a comforting illusion. Deep down, beneath the skin and the sheets, your atoms are behaving in ways that defy all common sense. Welcome to the Midnight Shift with the Sleepless Scientist. Tonight, we're going to explore the paradoxes of the quantum realm, not to solve them, but to let their strange, fuzzy nature lull you into a heavy rest. It is a place where particles can be in two places at once, and where walls are merely suggestions. But the math can wait for tomorrow. For now, just listen to the hum of the universe and let the uncertainty wash over you. Let us step into the laboratory of your mind. It is not the bright, sterile lab of a daytime documentary with lens flares and upbeat electronic music. No, this is the Midnight Lab. The lights are dimmed low, casting long shadows against the brushed concrete walls. The only sound is the rhythmic, mechanical hum of a cooling fan spinning inside a server rack in the corner, a white noise that fills the room like a heavy gas. On the slate desk in front of you sits a ceramic mug of coffee that you poured hours ago. It is cold now. A thin, oily film has formed on the surface, a testament to the inevitable march of thermodynamics. You might look at that cold coffee and think it is still. It sits there, a black pool of caffeine and regret, seemingly motionless. But that is the lie of the macroscopic world. If you were to shrink down, dissolving your consciousness into something smaller than a grain of pollen, smaller than a virus, you would see that the coffee is a violent, chaotic riot. The water molecules are crashing into each other at hundreds of miles per hour, vibrating with kinetic energy even as the liquid cools. This is the thermal jitter, the background noise of existence. Nothing is ever truly still. Even the pillow beneath your head, which feels so stable and cool, is buzzing with atomic vibration. The cotton fibers are made of cellulose chains, and within those chains, carbon and oxygen atoms are dancing a jittery waltz that never ends. You are resting your head on a swarm of motion. But tonight, we're going to go deeper than just vibrating atoms. We are going to descend into the basement of reality, down to the quantum level, where the rules of physics stop acting like strict laws and start acting like casual suggestions. The deeper we go, the stranger the neighborhood becomes. In the daylight world, if you throw a tennis ball at a wall, it bounces back. That is reliable. That is classical physics. It is the physics of car crashes and falling apples, and why you shouldn't jump off a roof. But down here, in the subatomic basement, things are different. Down here, if you throw a tennis ball at a wall, sometimes it bounces back, sometimes it decides it was actually on the other side of the wall the whole time. Imagine for a moment that we can cool this laboratory down. We are going to lower the temperature, stripping away the heat, stripping away the energy. We turn a dial, and the room drops to freezing. Then past the temperatures of an Antarctic winter. Then past the temperature of deep space. We are approaching absolute zero. Negative 273.15 degrees Celsius. At this temperature, the chaotic dance of the atoms begins to slow. The frantic vibrating of the coffee molecules calms down. The air in the room turns into a liquid, then a solid, falling as nitrogen snow. It is a quiet, unlike anything you have ever heard. In the real world, silence is just the absence of noise. But here, near absolute zero, silence is the absence of motion. It is a deep, heavy stillness where time itself seems to get sluggish, like syrup pouring on a winter morning. In this extreme cold, we encounter the first strange comfort of the quantum realm. Identity starts to dissolve. When atoms get cold enough, they stop acting like individuals. They lose their distinct edges. They clump together into a single state of matter called a Bose-Einstein condensate. Imagine a crowded room where suddenly everyone stops being an individual person and melts into a single collective consciousness. That is what happens to matter. It is a cosmic mosh pit where you are the floor and the floor is you. It is a terrifying thought for the ego, but a relaxing one for the weary mind. Down here, there is no pressure to be unique. There is no pressure to stand out. You are just a waveform, overlapping with everything else, resting in the lowest possible energy state. A great, cold slumber of the elements. But we cannot stay in the freezer forever. We have to turn the dial back up, let the heat return, and watch the particles wake up and start their nonsense again. While your coffee grows cold on the desk, the particles within the mug are beginning to behave in ways that would ruin a physicist's evening. Let us look at light. You have probably been told that light is a wave, or maybe you heard it is a particle. The truth is, light is an erotic mess that cannot make up its mind. This brings us to the most famous, and perhaps the most frustrating, experiment in the history of science, the double-slit experiment. Visualize a dark room. It is completely pitch black, save for a single sophisticated device sitting on a table. It is a gun, but not the kind that fires lead. This is a photon gun. It is designed to fire a single particle of light at a time. Just one tiny packet of energy. A lonely spark in the dark. In front of this gun, we have placed a barrier, a simple plate of metal with two vertical slits cut into it, two narrow doorways side by side. Behind the barrier is a detector screen that will light up whenever a photon hits it. Now, engage your common sense. If you were standing there with a handful of marbles and you threw them at the two slits, some would bounce off the metal and some would go through. On the wall behind, you would expect to see two piles of marbles, one pile behind the left slit and one pile behind the right slit. This is logic. This is how the world works when you are driving a car or pouring sand. So, we turn on the photon gun. Click. One particle fires. It passes through a slit and hits the back screen. Click. Another one. Click. Another. We sit in the dark, listening to the slow, rhythmic firing of the machine. It is a hypnotic sound, like a clock ticking in an empty house. We let it run for an hour, sipping our cold coffee, waiting for the pattern to build up. When we finally check the screen, we expect to see two bands of light corresponding to the two slits, but we do not. Instead, we see a series of many bands, light and dark, rippling out across the screen. It looks like the pattern ripples make in a pond when you throw two stones in at once. The waves interfere with each other. Where two crests meet, they get bigger. Where a crest meets a trough, they cancel out. This means the light is behaving like a wave. It went through both slits at the same time. interfered with itself, and landed on the screen. But wait, we fired them one by one. A single particle. How can a single particle go through two different doors at the exact same time? How can one tiny speck of light interfere with itself? It is like you walking through your front door and your back door simultaneously and then high-fiving yourself in the living room. It should not be possible. This is the first true headache of the night. The particle exists in a state of probability. Until it hits the screen, it is not really a thing in a specific place. It is a ghost. It is a smear of possibility. It is everywhere and nowhere. It travels through the left slit, the right slit, neither, and both, all at once. But here is where the universe gets shy. Physicists, being control freaks, decided they wanted to know which slit the photon actually went through. So they put a sensor right next to the slits, a tiny quantum camera to watch the door and say, aha, it went through the left one. So we set up the experiment again. The dark room, the photon gun, the metal plate. But this time, we are watching. We turn on the machine. Click, click, click. The photons fly. The sensor beeps, recording which path each particle takes. Left, right, right, left. We feel smug. We have caught nature in the act. We know where the light is going. But when we look at the back screen to see the pattern, our hearts sink. The interference pattern is gone. The ripples have vanished. Instead, there are just two boring bands of light, two piles of marbles. By simply watching the particle, we forced it to choose. We bullied it into acting like a solid object. The moment we looked, the wave collapsed. The ghost became a grain of sand. This is the observer effect. It suggests that the universe changes its behavior depending on whether or not it is being watched. Think about that as you lie in the dark, the chair in the corner of your room, the shoes by the door, the dust motes floating in the air. Are they really there in the sharp, defined way you think they are? Or are they just fuzzy waves of probability waiting for your eye to interact with them so they can snap into position? It gives a whole new meaning to the phrase, out of sight, out of mind. In the quantum world, out of sight means out of reality, or at least reality becomes a very loose concept. It is as if the universe is a video game that only renders the graphics when you turn your character to look. Behind you, the world is just wireframes and code. This duality, this refusal of light to be just one thing, is a lot like the flickering of a distant neon sign in a rainy alleyway. You know the kind. A lonely, open sign buzzing in the window of a diner at 3 in the morning. Sometimes the gas inside the tube glows steady and bright, a wave. Sometimes it flickers and spits, individual sparks jumping across the gap, particles. It is both, and it is neither. It depends on the voltage, the temperature, the age of the glass. The photon is just as indecisive. It has stage fright. When it is alone in the dark, it dances freely, flowing like water. But the moment the audience lights come on, it freezes, stands at attention, and acts like a proper little soldier of matter. If light cannot decide what it is, then the objects we touch are far less solid than they appear. The atoms in your hand, the atoms in the sheet covering you, they are all made of these indecisive particles. You are built from billions of tiny ghosts that only pretend to be solid because there are so many of them doing it at once. This leads us to a very crowded, very uncomfortable box. If a single particle can be in two states at once, a wave and a particle here and there, what happens if we scale that up? What happens if we take that quantum weirdness and apply it to something we can see, something we can pet? Enter Erwin Schrödinger, an Austrian physicist who in 1935 came up with a thought experiment that has been keeping cat lovers awake for nearly a century. Schrödinger did not actually put a cat in a box. He was a theoretical physicist, which means he did his damage with a pen and paper, not with actual animals. But the scenario he crafted is the perfect bedtime story for the cynical realist. Here is the setup. We have a sealed steel chamber, a heavy lead-lined box. You cannot see inside. You cannot hear inside. It is completely cut off from the rest of the universe. Inside this box, we place a few items. First, a Geiger counter, a device that detects radiation. Second, a tiny amount of a radioactive substance so small that in the course of an hour, there is a 50-50 chance that one of the atoms will decay and release a particle. Just one atom. If the atom decays, the Geiger counter detects it. The counter is rigged to a hammer. If the counter clicks, the hammer drops. Beneath the hammer is a flask of hydrocyanic acid, poison. If the hammer drops, the flask shatters, the poison is released, and, well, it is a bad day for the occupant of the box. The occupant is a cat. Let us call him Mittens. So, we seal the box, we set a timer for 1 hour, and we wait. During that hour, we are outside the box, sitting in our midnight lab, listening to the fan hum. We have no way of knowing what has happened inside. Remember the rule of the quantum realm. Until you measure it, the particle is in a state of probability. The atom has both decayed and not decayed. It is a wave of possibility. Because the atom drives the Geiger counter, and the counter drives the hammer, and the hammer drives the poison, the state of the cat is entangled with the state of the atom. According to quantum mechanics, until we open the box and look, Mittens is not dead. He is not alive either. He is in a state of superposition. He is both dead and alive at the same time. The universe has not decided yet. This is the deglamorized reality of superposition. It is not a magical state of being everywhere. It is a state of existence that is essentially a cosmic shrug. The universe is saying, I don't know, and I won't know until you force me to check. This concept is deeply disturbing to our human brains. We live in a binary world. You are awake or you are asleep. The light is on or it is off. The cat is purring or it is decomposing. We do not like the middle ground. The middle ground feels like madness. But in the math of the quantum world, that middle ground is the only place that matters. Imagine the box sitting there on the table. It is heavy, cold steel. Inside, there is a reality that is blurry. It is like a photograph that hasn't finished developing. The cat is a ghost suspended between two destinies. Now, extend that thought to your own life. How many boxes are sealed around you right now? The email you sent that hasn't been read yet? Is the recipient angry or happy? Until they read it, they are both. The lottery ticket in the trash can, is it a winner or a loser? Until you check the numbers, it is a piece of paper worth millions and zero simultaneously. There is a strange, philosophical comfort in this. We worry so much about outcomes. We stress about the future, but the quantum realm tells us that the future is not written in stone. It is not even written in ink. It is written in smoke. Until a choice is made, until an observation occurs, every possibility is still breathing. The bad outcome has not happened yet. The good outcome has not happened yet. They are just potential, floating in the dark. Eventually, though, we have to open the box. The hour is up. We lift the heavy steel lid. The hinges creak. We peer inside. Instantly, the wave function collapses. The blurriness snaps into focus. Nature is forced to choose. We see either a living, breathing cat looking very annoyed, or we see a tragedy. But we never see both. The act of looking forced the universe to make up its mind. Schrödinger actually hated this interpretation. He came up with the cat example to show how absurd quantum mechanics was. He wanted to say, look how stupid this is. Obviously, a cat can't be both dead and alive. He was trying to mock the theory, but the joke was on him. The more we tested the math, the more we realized that while it is absurd for a cat, it is absolutely true for the particles that make up the cat. But even if we leave the cat alone, letting the poor thing exist in its dual state, the particles themselves are having conversations across the universe without ever saying a word. This brings us to a phenomenon that Einstein called spooky action at a distance. He did not call it that because he was trying to be poetic. He called it that because he was genuinely creeped out. It offended his sense of order. Einstein liked rules. He liked speed limits. He believed that nothing could travel faster than the speed of light. If something happened over here, it would take time for the news to travel over there. But the quantum world does not care about Einstein's feelings. Let us talk about entanglement. This is the idea that two particles can share a single soul across light years of empty space. Imagine we have two electrons. We bring them together in our lab, let them interact, and through a delicate dance of physics, they become entangled. Their properties are now linked. For example, electrons have a property called spin. It is not exactly spinning like a top, but for the sake of our midnight visualization, let's say it is. One spins up and the other spins down. Because they are entangled, they must always have opposite spins. If one is up, the other must be down. It is a law of conservation. The universe keeps the books balanced. Now, we separate them. We put one electron in a trap here in our lab. We put the other electron in a rocket ship and send it to the other side of the galaxy. Let's say to a lab on a planet orbiting Proxima Centauri, 4 light years away. So, we wait 4 years for the ship to arrive. Now, we have one electron here, hovering in a magnetic field in front of us. And we have its partner 4 light years away, sitting in an alien lab. Here is the spooky part. Remember, until we measure them, these particles are in superposition. They are spinning both up and down at the same time. They are undecided. But the moment, the exact nanosecond, we measure our electron here on Earth, something impossible happens. Let's say we look at our electron and we find it is spinning up, instantly, faster than the speed of light, faster than a text message, faster than instantaneous. The electron at Proxima Centauri decides to spin down. It knows, somehow, across the vast, freezing void of 4 light years, the information traveled instantly. It is as if they are not 2 separate particles at all, but the same object stretched across space. Einstein hated this. He argued that there must be hidden variables, secret instructions inside the particles that we just couldn't see. He compared it to a pair of gloves. If you put one glove in a box and mail it to Antarctica, and you keep the other one, if you open your box and see a left glove, you instantly know the one in Antarctica is a right glove. No magic there, just logic. But quantum mechanics is not about gloves. It was proven later, through a theorem by a physicist named John Bell, that the particles do not have hidden instructions. They really are deciding in the moment. They are genuinely flipping a coin, and somehow the coins always land on opposite sides, no matter how far apart they are. Visualize those 2 electrons, tiny shimmering specks of charge. One is here, in the cool air of your room. The other is drifting in the silence of deep space. A dark, velvet void separates them. But there is an invisible thread, a connection that ignores distance, ignores time, ignores the speed of light. They are dancing together in the dark. It suggests that separation is an illusion. We look at the universe and see separate objects. A star here, a planet there, a person here, a person there. We see gaps. We see empty space. But in the eyes of the math, once 2 things have met, once they have interacted, they are never truly apart. Their wave functions are mingled. Think about the atoms in your body. They were forged in the hearts of dying stars billions of years ago. They have bounced against billions of other atoms in nebulae, in asteroids, in the atmosphere of early Earth. How many of your atoms are entangled with things you will never see? Maybe a carbon atom in your left hand is entangled with a hydrogen atom drifting in the atmosphere of Jupiter. Maybe the iron in your blood is dancing in sync with a particle buried in the ice of a comet. You are not an island. You are a web, a sprawling, invisible web of connections that stretches out into the cosmos, tying you to the fabric of reality in ways you cannot feel, but are nonetheless true. This invisible connection is a bridge, and sometimes particles decide to cross bridges that aren't even there. We have talked about particles being in 2 places, and particles talking faster than light. Now, let us talk about particles walking through walls. This is called quantum tunneling. In the classical world, the world of oat milk lattes and fire codes, if you run at a concrete wall, you will stop. You will hit the wall, you will bruise, and you will likely fall over. This is because the electrons in your body repel the electrons in the wall. It is an electromagnetic force field that feels like solid matter. But if you were an electron, the wall would look different. It would not look like a solid barrier. It would look like a hill, an energy hill. Now, if you roll a ball up a hill and you don't give it enough energy, it won't make it to the top. It will roll back down. That is classical physics. You need enough energy to overcome the barrier. But in the quantum world, the particle is a wave, and waves are fuzzy. They don't have a hard location. A wave extends out. It has a tail that trails off into the distance. So when an electron approaches an energy barrier, a wall, most of its wave bounces off. But a tiny, tiny piece of that wave, the tail, might extend through the barrier to the other side. Because the particle's location is based on probability, there is a small, non-zero chance that the particle will simply appear on the other side. It does not climb over the wall. It does not bore a hole through the wall. It simply ceases to exist on one side and instantly exists on the other. It tunnels through the impossible. This sounds like science fiction, like a cheat code in a video game. But it is happening inside you right now. Your DNA, the double helix script that writes your biology, is held together by hydrogen bonds, protons. Sometimes, very rarely, a proton in your DNA will quantum tunnel across to a place it shouldn't be. It slips through the barrier. When your DNA replicates, this misplaced proton can cause a mutation, a typo in the code. Most of the time, this does nothing. Sometimes it causes problems, but sometimes, over billions of years, these tiny quantum jumps, these ghosts walking through walls, are the reason evolution happens. You are here, lying in bed, capable of understanding these words, partly because billions of years ago, subatomic particles decided to ignore the no trespassing signs of physics and walk through a wall. It is a survival strategy written in the language of chance. Imagine trying to walk through a closed door yourself. You stand there, pressing your hand against the wood. In the quantum view, there is a probability, infinitesimal but real, that all the particles in your body could simultaneously tunnel through the door. If you waited long enough, longer than the age of the universe, longer than the lifespan of the stars, eventually, statistically, you would fall right through the wood and land in the hallway. So, walls are not absolutes. They are just probability spikes. They are suggestions that usually hold up, but not always. The universe is porous. It is leaky. Nothing is truly sealed tight. The lead box we put the cat in, even that isn't perfect. Given enough time, the atoms of the box could tunnel out. The atoms of the cat could tunnel out. Everything is slowly leaking into everything else. The sardonic truth is that in the quantum world, no entry signs are merely suggestions for those who are small enough and patient enough. It seems the universe is shy, and it only behaves properly when it knows it's being watched by a curious eye. We return to the idea of the observer. We touched on it with the double-slit experiment, but let's go deeper into the philosophical horror of it. The Heisenberg uncertainty principle. Werner Heisenberg was a German physicist who realized that nature has a limit on precision. He discovered that there are pairs of properties that you cannot know simultaneously. The most famous pair is position and momentum. Position is where you are. Momentum is how fast you are going and in what direction. In our world, you can know both. Your GPS can tell you that you are on the highway, position, and that you are going 65 miles per hour. Momentum. Simple. But for a particle, you have to choose. If you measure the position of an electron with extreme precision, if you pin it down to a tiny, exact point, you lose all information about its momentum. It becomes a blur of motion. You know where it is, but you have no idea where it is going or how fast. Conversely, if you measure its momentum, you clock its speed perfectly, you lose all information about its position. It becomes a smear of location. You know how fast it is going, but you have absolutely no idea where it is. It is not that our instruments are bad. It is not that we need better microscopes. It is a fundamental property of the universe. The information simply does not exist. Imagine trying to take a photograph of a fast-moving ceiling fan in a dark room. You use a camera with a slow shutter speed. The photo shows a blurry circle of motion. You can see the speed, momentum, but you cannot see the individual blades' position. Now, use a high-speed flash. Snap. You freeze the blades in place. You can see exactly where they are, position, but in that frozen image, you have lost the sense of their motion, momentum. Nature refuses to be precise. It leaves us with a universe that is fundamentally out of focus at its core. We want crisp lines. We want clear answers. But the deeper we look, the more we realize that the foundation of reality is not a sharp architectural drawing. It is an impressionist painting. It is dots and blurs that only look like a picture when you stand far away. This blurriness is the fuzz of existence, and perhaps there is peace to be found in that. You are lying in bed, running through the checklist of your day. Did I lock the door? Did I turn off the oven? Did I say the wrong thing to that person? You are trying to measure the position and momentum of your life with absolute precision. You want to know exactly where you stand, but the universe tells us that you can't know. The more you try to pin down exactly where you are, the less you know about where you are going. The more you focus on the trajectory, the less grounded you are in the moment. It is a physical law that uncertainty is baked into the cake. You are allowed to be blurry. You are allowed to be unfocused. The atoms that make you up certainly are. Beneath that blurriness, the vacuum of space is not actually empty. It is a boiling sea of things that don't yet exist. We tend to think of a vacuum as nothingness. If we take a box and pump all the air out, pump all the dust out, shield it from radiation, and cool it to absolute zero, we think it is empty. But quantum mechanics laughs at the idea of empty. There is something called the quantum vacuum, or quantum foam. Even in perfect emptiness, the uncertainty principle says that energy cannot be exactly zero. Zero is too precise. Nature hates precise. So, the energy level fluctuates. It jitters. Out of this jitter, particles pop into existence. A particle and its antiparticle, matter and antimatter, suddenly appear out of nowhere. They borrow energy from the vacuum, exist for a fraction of a nanosecond, and then collide and annihilate each other, returning the energy to the vacuum. They are called virtual particles, but they are real enough to have effects. Imagine the empty space in your room right now, the space between your bed and the dresser. It looks empty, but it is actually a frothing, bubbling soup of creation and destruction. Particles are blinking in and out of existence like sparks from a dying campfire. Pop, pop, flash, gone, trillions of times a second. Everywhere. The vacuum is alive. It is heavy. It has pressure. If you were small enough to see it, the emptiness would look like a boiling pot of water. A chaotic storm of energy. There is a smell to this, if you could smell it. A metallic ozone scent. The smell of lightning. The smell of raw electricity. It is the smell of the universe working overtime just to look like it is doing nothing. It is exhausting to think about. The universe never sleeps. Even when there is nothing there, it is busy making sure that the nothing is fully populated with temporary somethings. But you, the macroscopic giant, you do not need to worry about the quantum foam. You float above it. You are a massive cruise ship sailing on top of this choppy, microscopic ocean. You do not feel the waves. You just feel the gentle sway of gravity. As the foam settles and the energy dips, we find ourselves back in the quiet, dark room of our own reality. We have toured the basement. We have seen the indecisive light, the zombie cat, the spooky telepathic electrons, and the ghosts walking through walls. It is a weird place. It makes no sense to our primate brains, which evolved to hunt on savannas and build shelters out of mud. We evolved to understand rocks and sticks, not wave functions and probability clouds. But there is a legacy of grit here. Think about what keeps you solid. You are made of atoms, electrons orbiting a nucleus. But the electron is negatively charged and the nucleus is positively charged. They should attract. The electron should spiral crash into the nucleus. The atom should collapse. You should collapse into a tiny speck of dense matter. Why don't you? Because of these quantum rules. The uncertainty principle forbids the electron from getting too close to the nucleus, because if it did, we would know its position too well, so it keeps its distance. It hums in a cloud around the center. It is this quantum refusal to be pinned down that gives atoms their size. It is what makes solid matter take up space. It is what keeps the floor solid beneath your bed. It is what keeps the air in your lungs. You are held together by the stubborn refusal of subatomic particles to follow the rules of classical logic. You are a walking paradox, a structure built on uncertainty, a solid object made of ghosts. And tonight, that is enough. You do not need to solve the equations. You do not need to collapse the wave function. You can just be. You can let your own thoughts become like the quantum foam, bubbling up and vanishing, popping in and out of existence without consequence. Let them be virtual thoughts. Don't grab them. Don't measure them. Just let them annihilate back into the vacuum. The cooling fan is still humming. The coffee is cold. The neon sign in the distance is flickering. You are here, and you are there. You are awake, and you are drifting. Close your eyes now. The particles will continue their strange dance without your supervision. And for tonight, that is enough. But perhaps that is a lie we tell ourselves to find comfort in the dark. Because deep down, in the folds of the gray matter that refuses to shut off, you know that the dance never really stops. And the implications of that dance are far stranger than just a ghost cat or a spooky electron. We have looked at the particles as if they are tiny actors on a stage, waiting for us to applaud so they can choose a role. But there is another theory, a theory that suggests the actors never choose. They play every role in every play all at once, forever. So, sit up for a moment, adjust the pillow. The night is still young, and we have to open the heaviest door in our midnight laboratory. We are leaving the cold steel room of the cat and the lead box. We are walking down a long, dimly lit hallway where the floorboards creak with the weight of infinite possibilities. We are entering the library of many worlds. In 1957, a doctoral candidate at Princeton named Hugh Everett III had a thought that was too heavy for the physics community to hold. He looked at the math of the quantum world, the math that says a particle is in two places at once, and he asked a simple, terrifying question. What if the wave function never collapses? What if the universe never chooses? When we opened the box to check on the cat, we assumed that reality snapped into one single outcome. The cat is alive, or the cat is dead. But Everett suggested that the universe is not a singular thing. He proposed that, at the moment of measurement, the universe splits. Picture a tree, a massive, ancient oak tree growing in the dark. The trunk is the timeline of the past. It is solid, it is wood and bark and memory. But as you move up the trunk to the present moment, the wood splits into branches. Every time a subatomic particle interacts with another, which happens trillions of times a nanosecond inside your own body, the branch splits. In one branch, the radioactive atom decayed, the hammer dropped, and the cat is dead. In another branch, the atom did not decay, the hammer stayed put, and the cat is alive. Both branches are equally real. Both versions of the cat are real. And, most disorientingly, both versions of you are real. This is the many worlds interpretation. It suggests that reality is constantly fracturing, like a pane of glass that never stops shattering. It is a concept that strips away the specialness of your current experience. You think you are the only you lying in that bed listening to this voice. But in the branch next door, separated by a membrane of probability thinner than a thought, there is a version of you who turned this video off 5 minutes ago. There is a version of you who decided to get a glass of water. There is a version of you who never bought the bed you are lying in. Let us visualize this as a library. Imagine a space that is infinite. The ceilings are lost in shadow. The shelves stretch out in every direction, miles upon miles of dark mahogany rows, smelling of dust and old paper and binding glue. Every book on every shelf is a biography of the universe. You are walking down an aisle. This aisle is your current timeline. It is the story where you are tired, your eyes are heavy, and you are trying to understand quantum mechanics. But if you look through the gaps in the shelves, you can see other aisles. In the aisle to your left, you are asleep. In the aisle to your right, you are wide awake, staring at the ceiling, worrying about a conversation from 3 years ago. The horror of the many worlds theory is not that you are alone. It is that you are never, ever alone. You are accompanied by an infinite army of almost yous. Think about the implications for a moment. It creates a sort of vertigo, a nausea of the soul. Every mistake you almost made, you actually made in another world. Every car accident you narrowly avoided, you didn't avoid in another branch. The universe is a hoarder's episode of realities. It throws nothing away. Every possibility, no matter how tragic or mundane, is kept and stored on a shelf in this infinite library. There is a strange, sardonic weight to this. We spend so much energy regretting our choices. If only I had taken that job. If only I hadn't said that. The sleepless scientist is here to tell you. You did. You took the job. You kept your mouth shut. You moved to the city. You stayed in the town. Somewhere in the vast branching fractal of the multiverse, those lives are playing out with the same visceral realism as this one. The coffee is just as cold there. The fan is just as loud. Does this make your choices meaningless? Not quite. It just makes them specific. You are carving a path through the library. You are choosing which aisle to walk down. The other aisles exist, but you don't have to read those books. You only have to read this one. And right now, the text on the page says, you are safe, you are warm, you are static. But let us shake the dust off that idea and look at something even stranger. If the universe is splitting constantly, what holds it together? What keeps the aisles from crashing into each other? It is a phenomenon called decoherence. It is the reason we don't see the other worlds. The vibrations of the different branches get out of sync. It is like two radio stations playing on frequencies that are drifting apart. For a brief moment, you can hear the static of the other song, but eventually, the signal clears and you are locked into your own broadcast. However, sometimes the signal doesn't clear. Sometimes the universe lets us manipulate time itself. We have talked about particles moving through space. Now, we must talk about particles moving through time, or rather, the illusion that time flows in one direction. In our macroscopic world of alarm clocks and deadlines, time is an arrow. It flies from the past to the future. You break an egg and it scrambles. You cannot unscramble it. This is entropy. It is the law of the land. But down in the quantum basement, the arrow of time is not so straight. In fact, it might be double-headed. Let me introduce you to the delayed choice quantum eraser. It sounds like a bad science fiction weapon, or perhaps a tool for removing ink from a page, but it is actually an experiment that suggests the future can change the past. We go back to the double-slit experiment. Remember the photon gun? Remember the mystery. If we don't watch, it behaves like a wave. If we do watch, it behaves like a particle. Physicists decided to get clever. They set up a complicated maze of crystals and mirrors. They fired a photon through the double slits. But this time, they split the photon into two entangled twins. One twin goes to a detector screen to make the pattern. The other twin goes off on a longer journey through a series of detectors that act as watchers. Here is the kicker. The experiment is set up so that the decision to watch or not watch the second twin happens after the first twin has already hit the screen. Read that again in your mind. The first particle hits the wall. It has made its mark. It is done. It is history. Then, nanoseconds later, we decide whether or not to check which path its twin took. Common sense screams that what happened second cannot affect what happened first. You cannot burn the toast after you have already eaten it, but the data disagrees. If we choose to destroy the information about the path, if we choose not to look at the twin, the first particle, the one that already hit the screen in the past, shows an interference pattern. It acted like a wave. If we choose to look at the twin, the first particle shows a clump pattern. It acted like a particle. The choice made in the future determine the history of the particle in the past. It is as if the particle arrived at the screen, waited, looked at its watch, and said, "Okay, are they going to look at my brother in 5 nanoseconds? If yes, I'll be a rock. If no, I'll be a ripple." This suggests that history is not a fixed recording. It is a fluid dynamic. The events of the past are entangled with the choices of the future. Lie there and let that sink into your bones. The past is usually a heavy thing. We carry it like a backpack full of bricks. We think it is written in stone. But in the quantum realm, the past is just as fuzzy as the future. It is a cloud of what might have happened that only sharpens when the future requires it to. It gives a whole new layer of meaning to the phrase, "Hindsight is 20/20." In quantum mechanics, hindsight actually constructs the view. Now, take a breath. The air in your room is cool. The shadows are long. You are not a photon. You are a biological machine made of trillions of cells, and you generally experience time in a straight line. You remember breakfast? You do not remember tomorrow's dinner. That is a limitation of your neurology, not necessarily a limitation of the universe. But let us pivot to something that feels a little less like a headache and a little more like a superpower or a curse, depending on how much you value your privacy. The quantum Zeno effect. Zeno was an ancient Greek philosopher who loved paradoxes. He said that if you shoot an arrow at a target, before it gets there, it has to go halfway. And before it goes halfway, it has to go a quarter of the way. And before that, an eighth. He argued that motion is impossible because you have to complete an infinite number of tasks to move an inch. Obviously, arrows do hit targets. Zeno was wrong about the macro world, but he was accidentally right about the quantum world. The quantum Zeno effect states that a system cannot change while you are watching it. Let's go back to our radioactive atom in the box with the cat. That atom is unstable. It wants to decay. It wants to spit out a particle and change into a different element. It is like a person holding a heavy box who desperately wants to drop it. But if we stare at the atom, if we measure it constantly, checking it 1,000,000 times a second, it will never decay. The act of observation freezes the system in its current state by asking, "Are you decayed yet?" Over and over again, we force the wave function to collapse back to the undeformed state. We reset the clock. "A watched pot never boils" is an old proverb about patience. In physics, it is a literal instruction for freezing time. If you could look at something fast enough, if you could observe it continuously without blinking, without a single gap in your attention, you could prevent it from ever changing. You could stop a bird in mid-flight not by grabbing it, but by looking at it so intensely that its atoms are not allowed to move to the next state. Of course, you cannot do this. You blink, your brain has a refresh rate. You are a biological creature with lag, but the universe does not blink. There are theories that suggest the reason certain particles remain stable for billions of years is that the universe is constantly observing them, locking them in place with a relentless cosmic stare. It is a claustrophobic thought, to be held in place by the gaze of the vacuum. But it is also a form of preservation. The stability of your body, the fact that your atoms don't just drift apart or decay into radiation, is partly due to the constant interactions, the constant measurements between the particles themselves. Your atoms are watching each other. They are keeping each other honest. They are holding hands in the dark and saying, "Stay here. Be iron. Be carbon. Don't fade away." It is a microscopic solidarity, a pact of existence. And speaking of existence, we have to talk about the fabric of space itself. We mentioned the vacuum foam, the boiling soup of nothingness. But what if we zoom in even further? What if we try to find the pixel size of the universe? This brings us to the Planck length. In our digital world, we are used to pixels. If you look at your phone screen with a magnifying glass, you see the tiny red, green, and blue squares. The image is not smooth. It is made of blocks. Scientists have asked, is the universe smooth? Is reality like a continuous oil painting, or is it a digital image made of tiny, discrete blocks? If you take a ruler and divide it in half, then divide that half and keep going, do you eventually hit a limit, a point where you cannot divide space any further? The answer seems to be yes. There is a length 1.6 times 10 to the power of negative 35 meters. It is called the Planck length. It is the resolution limit of the universe. It is the pixel size of reality. Below this length, the concepts of space and geometry break down. You cannot have a distance shorter than this. It is like trying to draw a line thinner than the tip of your pencil. The physics just stops making sense. This suggests that the universe is granular. It is not a smooth flow. It is a grid. A three-dimensional grid of tiny, tiny volumes. And if reality is a grid, if it has a pixel size, that sounds suspiciously like a simulation. I am not saying you are in a computer. That is a topic for a different kind of anxiety. But the physics does mimic the constraints of a processing system. There is a maximum speed, the speed of light. There is a minimum size, the Planck length. There is a limit to how much information can be packed into a region of space. This is the Bekenstein bound. It says that a finite volume of space can only hold a finite amount of information. You cannot pack infinite data into a hard drive, and you cannot pack infinite complexity into a region of the universe. This leads to the holographic principle. Imagine a soda can. The can is three-dimensional. It has volume, it holds liquid, but all the information about the brand, the ingredients, and the logo is printed on the two-dimensional surface of the label. Some physicists believe the universe is like that can. They propose that all the information that makes up our three-dimensional reality, you, the bed, the room, the stars, is actually stored on a two-dimensional surface at the edge of the universe. We might be holograms, not the flickering blue ghosts from Star Wars, but a projection, a three-dimensional rendering of two-dimensional data. If this is true, then depth is an illusion. The feeling of reaching out and touching the wall is a sensory trick. In reality, you and the wall are just data points smeared on a distant horizon, interacting on a flat surface, projecting the experience of space. It sounds insane. It feels insane. You feel thick. You feel heavy. You feel the depth of your lungs as you breathe. But remember, your feelings are just electrical signals. Your brain is a dark, wet cavern that has never seen the light of day. It sits in your skull, receiving impulses from your nerves and constructs a story called the world. If the data coming in says there is depth, the brain builds depth. It does not care if the data comes from a 3D universe or a 2D surface. It just renders the scene. So, you are lying in a hologram generated by a pixelated universe, floating in a quantum soup, observing yourself into existence. It is a lot to take in on a Tuesday night, but let's ground this again. Let's pull back from the edge of the cosmic horizon and return to something tangible, something biological. Your nose. Take a breath. What do you smell? Maybe the faint scent of laundry detergent on the pillowcase. Maybe the stale coffee. Maybe the rain outside. Smell is a chemical sense. We used to think it was a simple lock and key mechanism. A scent molecule floats into your nose, fits into a receptor shape like a key in a lock, and triggers a signal. Shape matches shape. Simple. Classical, but there was a problem. Some molecules had the exact same shape but smell completely different, and some molecules have completely different shapes but smell exactly the same. The lock and key theory had holes in it. Enter the vibration theory of olfaction. This theory suggests that your nose is not just feeling the shape of the molecule, it is listening to it. The bonds between atoms in a molecule vibrate. They hum at specific frequencies. The theory proposes that when a scent molecule enters a receptor in your nose, an electron in the receptor quantum tunnels across the molecule. It uses the molecule as a bridge, but it can only cross the bridge if the molecule is vibrating at the right frequency. If the vibration matches, the electron tunnels, the signal fires, and you smell rose or burnt toast or wet dog. Your nose is a quantum spectroscope. You are literally sniffing the vibrations of atoms. You are detecting the quantum hum of matter with your face. It is a reminder that these strange high-level physics concepts are not just out there in the Large Hadron Collider or in black holes. They are intimate. They are happening in your nostrils right now. The smell of the room is a quantum event. This biological reliance on the weirdness of physics brings us to the concept of the quantum robin. No, not a superhero sidekick. The bird. The European robin. These birds migrate thousands of miles every year. They navigate with precision, even on cloudy days. We have known for a long time that they can sense the Earth's magnetic field. They have an internal compass, but biological material is wet and warm and messy. It shouldn't be able to detect something as weak as the Earth's magnetic field. A compass needle needs to be magnetic metal. Birds are made of meat. The answer lies in their eyes. Inside the robin's retina, there is a protein called cryptochrome. When blue light hits this protein, it creates a pair of entangled electrons. There they are again, entangled particles. The spooky handshake. These electrons are highly sensitive to magnetic fields. As the bird flies, the Earth's magnetic field tugs on these entangled electrons, altering their chemical reaction rates. This allows the bird to literally see the magnetic field. It likely appears as a band of light or color superimposed over their vision. They are flying through a heads-up display powered by quantum entanglement. Nature figured out quantum mechanics millions of years before we did. While we were banging rocks together, birds were using spooky action at a distance to find their way south for the winter. It is humbling. We think we are the masters of the domain because we built the microchip, but the trees, the the birds and even the bacteria have been exploiting the loopholes of reality for eons. Photosynthesis, the process that powers nearly all life on Earth, is a quantum cheat. When a plant cell catches a photon of sunlight, it needs to transport that energy to the reaction center to turn it into food. It has to navigate a maze of chlorophyll molecules. If the energy moved like a classical ball, bouncing randomly, it would lose too much energy before it got to the destination. It would be inefficient. Plants would starve. Instead, the energy moves like a quantum wave. It takes all possible paths at once. It explores every route simultaneously, finds the most efficient one, and collapses into that path. It is perfect efficiency. The grass outside your window is performing quantum computations every split second. To feed itself, the salad you ate for lunch was powered by the multiverse. It seems that life is not separate from the quantum realm. Life is a surfer riding the quantum wave. We exist in the warm, wet, chaotic middle ground where the impossible becomes the biological. So, as you lie there, feeling the heaviness of your limbs, realize that you are a masterpiece of improbability. You are a collection of atoms that should have fallen apart, held together by uncertainty, powered by quantum tunneling, and navigating a universe that might be a hologram. And yet, you are tired. The complexity of the hardware does not change the simplicity of the user experience. You just want to sleep. And that is the ultimate paradox. The universe is infinitely complex, terrifyingly strange, and fundamentally unknowable. But it is also boring enough to let you nap. The fan hums. The refrigerator compressor kicks on in the kitchen, a mundane rumble caused by gas compression and electric motors. But inside the copper wires of that motor, electrons are drifting. Inside the gas, molecules are colliding. Let's drift further out now. We have looked at the very small. We have looked at the very weird. Now, let's look at the very final. The black hole information paradox. This is the ultimate trash compactor of the universe. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. It is a one-way door. For a long time, we thought black holes were simple eaters. They ate matter, they grew bigger, and that was it. Stephen Hawking changed that. He realized that black holes are not completely black. They glow faintly. They emit radiation, thermal radiation. This is now called Hawking radiation. This means that black holes slowly lose energy over unimaginable timescales, numbers so big that writing them out would fill the rest of this script with zeros. Black holes will evaporate. They will shrink and eventually disappear. But here is the problem, the paradox that keeps physicists reaching for the aspirin. Quantum mechanics has a strict rule. Information is never destroyed. If you burn a book, the information is not gone. It is scrambled into the ash and the smoke and the heat. Theoretically, if you could collect every particle of ash and every photon of heat, you could reconstruct the book. The information is conserved. But if a book falls into a black hole, and the black hole eventually evaporates into random radiation, where did the book go? The radiation coming out of the black hole does not seem to carry the information of what fell in. It is just random heat. So, if the black hole disappears, the information of the book is gone forever, deleted from the universe. This violates the laws of quantum mechanics. But if the information is preserved, it violates our understanding of gravity. This is the war between general relativity, the laws of the big, and quantum mechanics, the laws of the small. They do not get along. They are like two roommates who hate each other but have to share a studio apartment. There are many proposed solutions to this paradox. Maybe the information is stored on the surface of the black hole. The hologram idea again. Maybe the information leaks out in subtle ways we can't measure yet. Or maybe, and this is the sleepless scientist favorite, the information goes somewhere else. Maybe the black hole is not a dead end. Maybe it is a bridge, a wormhole, an Einstein-Rosen bridge. What falls into a black hole in this universe might spill out into another universe. A white hole somewhere else, spewing out the contents of our reality into a new space. It is a beautiful image. The death of a star here is the birth of a galaxy somewhere else, a cosmic recycling system. It suggests that nothing is ever truly lost. It just moves. It changes address. The memories you have forgotten, the keys you lost in 2014, the dreams that faded as soon as you woke up, maybe they aren't gone. Maybe they just fell through the cracks of the floorboards and landed in the basement of a different reality. It is a comforting thought for the weary mind. You don't have to hold on to everything. You don't have to be the archivist of your own life. You can let things go. You can let them fall into the event horizon of sleep. The universe will catch them. It never drops anything. The Midnight Lab is quiet now. We have made a mess on the chalkboard. We have drawn diagrams of splitting universes, tunneling electrons, and holographic horizons. The dust of the chalk is floating in the air. Let's wipe the board clean, not because the science is wrong, but because the science is exhausting. The brain needs a break from the infinite. It needs the finite. It needs the pillow. Let's focus on the sensation of gravity again. Gravity is the one force we haven't managed to fit into the quantum puzzle. We have a theory for electromagnetism. We have theories for the nuclear forces, but gravity remains stubborn. It refuses to be quantized. It is smooth. It is heavy. It is undeniable. Feel it pulling on you. It is the most constant hug you will ever receive. It pulls your shoulders down away from your ears. It pulls your eyelids down over your eyes. It pulls the blood into your back where it meets the mattress. Gravity is the anchor. While your mind floats off into the multiverse, your body stays here. It stays on Earth. It stays in bed. It is the tether that keeps you from dissolving into the quantum foam. There is a concept in meditation called grounding. In electronics, grounding means providing a safe path for excess current to flow into the earth. In the human experience, it means the same thing. You are full of excess current right now. Excess thoughts, excess worry, excess data. Let the gravity be your ground wire. Visualize the static electricity of your day, the conversations, the screens, the traffic, draining out of your body, flowing down through the mattress, through the floorboards, through the concrete foundation, and into the soil of the earth. The earth is big enough to take it. It can handle your static. It has been spinning for 4.5 billion years. It has seen dinosaurs and ice ages and meteor impacts. It can handle your stress about the email you didn't send. Let it go. Listen to the silence of the room again. Is it truly silent? If you listen closely, past the ringing in your ears, past the hum of the appliances, you might hear the vacuum fluctuation, the hum of the nothing. It is a white noise that has been playing since the Big Bang. It is the sound of the universe breathing in and out, expansion and contraction. The universe is expanding, you know. Dark energy is pushing the galaxies apart. The space between things is getting bigger. Every second, the distance between us and the edge of the visible universe grows. We are becoming more isolated. The sky will eventually, in trillions of years, become dark as the other galaxies move beyond our sight. That sounds lonely. But tonight, let's reframe it. It is not loneliness. It is privacy. The universe is drawing the curtains. It is turning down the lights. It is creating a quiet, private space for our galaxy to rest. You are in a private space too. Your room is a sanctuary, a pocket universe where the laws of social interaction and productivity are suspended. In here, you don't have to be a photon. You don't have to be a wave or a particle. You don't have to choose a path. You can just exist in a state of rest. The ancients believed that sleep was a journey to the underworld, a nightly visit to the land of the spirits. We know now that it is a biological maintenance cycle. It is a defragging of the hard drive. It is a flushing of toxins from the brain tissue. But the science doesn't make it less magical. The fact that you can lose consciousness for 8 hours, hallucinate vivid stories, and then wake up refreshed and rebooted is a miracle of biology. It is the closest we get to time travel. You close your eyes and instantly, hours pass. You skip forward in time. Tonight, you are a time traveler preparing for launch. The capsule is your bed. The destination is tomorrow morning. But the launch sequence is slow. There is no countdown. There is just a gradual fading of the lights. Let's do a final check of the systems. Your feet, are they relaxed or are they still ready to run? Let the tension melt out of the arches. Let the toes uncurl. The running is done. Your hands, are they clenched? Are they holding on to the phone or the sheet or a worry? Open them. Let the fingers drift apart. The holding is done. Your jaw, the strongest muscle in the face. It holds so much unspoken language. Unclench it. Let the teeth part slightly. The talking is done. Your eyes, the observers, the tools that collapse the wave function. They have seen enough photons for one day. Close the shutters. Stop the measurement. Stop the collapse. Let the world go back to being a wave. Let the room around you dissolve into probability. You don't need to know where the chair is right now. You don't need to know where the door is. Let them be fuzzy. Let them drift. You are entering the superposition state. You are drifting between wakefulness and sleep. You are both and neither. It is a comfortable gray, a soft fog. Imagine yourself floating in that quantum liquid we talked about earlier, the Bose-Einstein condensate, the super cold fluid where individual atoms lose their identity and move as one. You are weightless. You are frictionless. You are cool and still. The noise of the day is just a ripple on the surface far above you. You are sinking deeper into the calm, dark depths where the water is still. Down here, the logic of the day does not apply. You don't need to make sense. Dreams don't make sense. They are quantum narratives. They jump from place to place. They change characters. They ignore time. Dreams are the brain's way of playing with the many worlds theory. Tonight, you might visit a world where you can fly, or a world where you live in a house you've never seen. Enjoy the travel. The Sleepless Scientist is signing off. The lab is closing down. We are flipping the switches on the server racks. The cooling fans are spinning down. The lights are clicking off, bank by bank. Click, click, click. The darkness is total now. But it is not empty. It is full of potential. It is full of rest. You are safe in the dark. You are part of the dark. Your atoms are humming a lullaby that is 13.8 billion years old. Listen to it. Let go. Sleep. But perhaps the sign-off was premature. The silence of the room can be loud, and sometimes the brain refuses the command to shut down. If you are still listening, if the gravity of the mattress has not yet pulled you into the unconscious, then we must go deeper. We must restart the cooling fans. We must reignite the pilot light of the laboratory. Because there are darker corners of the quantum basement we have not yet swept with our flashlight. Places where matter does not just act weird, but acts with a kind of malicious compliance to the laws of physics. So, keep your eyes closed. We are going to lower the temperature of the lab again. We are going back down to the place where heat dies, because that is where the liquids start to misbehave in a way that would give a hydrodynamics engineer nightmares. We are going to talk about superfluids. Imagine a cup of coffee sitting on that slate desk of yours. You stir it with a spoon. The liquid swirls around. Eventually, the swirling stops. The friction between the liquid and the cup, and the friction between the molecules of the coffee itself, drains the energy. The vortex dies. The coffee becomes still. This is viscosity. It is the internal friction of a fluid. It is why swimming through molasses is harder than swimming through water. But in the quantum realm, there is a substance called liquid helium-4. If we cool this helium down to near absolute zero, it undergoes a phase change. It stops being a normal fluid and becomes a superfluid. And a superfluid has zero viscosity. None. It has zero friction. If you stirred a cup of superfluid coffee, it would never stop swirling. It would rotate forever. 1,000,000 years from now, that vortex would still be spinning with the exact same speed as the day you stirred it. It is a perpetual motion machine in a cup. But it gets creepier. Because it has no friction, a superfluid does not like to be contained. If you put it in a beaker, it will form a thin film that creeps up the walls of the glass. It climbs against gravity. It crawls up the side, over the rim, and drips down the outside of the container until the beaker is empty. Picture that in the dark. A liquid that refuses to stay in the cup. A zombie fluid that silently escapes its prison by crawling up the walls. like a wet ghost. It flows through pores in ceramic that are so small even air molecules cannot get through. It is the ultimate escape artist. It behaves this way because at these temperatures, the helium atoms have lost their individuality. They have become that Bose-Einstein condensate we mentioned earlier. They are all marching in perfect lockstep. If one atom moves, they all move. It is a fluid with a hive mind. So, as you lie there, be grateful for friction. Be grateful that the water in your glass stays in your glass. Be grateful that your blood has viscosity and pumps through your veins with resistance. Friction is the force that allows us to grip the world. Without it, everything would be a slippery, sliding chaos, flowing endlessly without purpose. Friction is the drag that slows you down, but it is also the traction that lets you move forward. It is a paradox you can feel in your sheets. The friction of the cotton against your skin is what keeps you warm. It is what keeps the blanket in place. Now, let us shift our gaze from the fluids that flow forever to the particles that refuse to touch. We talked about how you are mostly empty space and how quantum rules keep you solid, but we need to give a name to the sheriff of that town. We need to talk about the Pauli exclusion principle. Wolfgang Pauli was an Austrian physicist known for being a brutal critic. He once dismissed a bad paper by saying, "This isn't right. It's not even wrong." He demanded rigor, and the principle named after him is the most rigorous rule in the universe. It states that two identical fermions, particles like electrons, protons, and neutrons, cannot occupy the exact same quantum state at the same time. Think of it as a parking lot with very strict rules. Each parking space can only hold one car. If a car is already in the spot, you cannot park there. You have to find another spot, one level up or one level down. This sounds simple, but it is the reason you are not collapsing into a black hole right now. The electrons in your atoms are fermions. They are the cars. As gravity tries to crush your atoms together, the electrons resist. They say, "No, this spot is taken. You cannot come here." They push back, not with an electric force, but with a degeneracy pressure. It is a pressure born purely from the rule that says, "I am here, so you must be there." It is the ultimate social distancing. Electrons refuse to share their personal space. This refusal is powerful. It is strong enough to hold up a star. When a star like our sun eventually dies and collapses, it will turn into a white dwarf. A white dwarf is a star packed so tight that a teaspoon of it weighs as much as a truck, but it stops collapsing. Why? Because of the electron degeneracy pressure. The electrons are screaming, "Back off." It is a comforting thought. The structural integrity of your body, the hardness of the floor, the strength of the steel in the buildings around you, it all comes down to the stubbornness of subatomic particles refusing to share a bunk bed. You are built on a foundation of exclusion, a microscopic boundaries policy that has been enforced since the dawn of time. But not all particles are fermions. Some are bosons. Bosons are the hippies of the particle world. They do not follow the Pauli exclusion principle. They love to share. You can pack 1 trillion bosons into the same quantum state, and they will happily sit right on top of each other. Photons, particles of light, are bosons. That is why you can shine two flashlights' beams through each other and they don't bounce off. They just pass through. That is why lasers work. You can stack infinite light into a single beam. So, the universe is divided into two camps: the isolationists who build structure, matter, and the collectivists who carry force, light. It is a delicate balance between the hard, stubborn stuff that makes you and the soft, overlapping stuff that lets you see. Speaking of things that pass through you, let us talk about the ghost stream. Right now, as you lie in the dark, you are being bombarded. You are being riddled with bullets, but you cannot feel them. They are called neutrinos. Neutrinos are subatomic particles that are born in the nuclear furnace of the sun. Every time 4 hydrogen nuclei fuse to make helium in the sun's core, they release neutrinos. These particles are incredibly antisocial. They have almost no mass. They have no electric charge. They do not feel the strong nuclear force. They barely feel gravity. To a neutrino, solid matter is smoke. It is less than smoke. To a neutrino, the Earth is not a rock. It is a thin fog. They fly straight through the planet without even slowing down. Every second, about 65 billion neutrinos pass through every square centimeter of your body. 65 billion every second. Through your thumbnail. They are passing through your roof, through your skull, through your brain, through the bed, through the floor, through the crust of the earth, through the molten iron core, and out the other side into space. And you feel nothing. They are the ghost particles of the universe. They are the silent witnesses. They were there at the beginning of the universe, and they will be there at the end, flying through the void, untouched and untouching. Occasionally, very occasionally, a neutrino will hit an atom in your body. But it is so rare that you would have to wait years for it to happen once. And even then, it is just a tiny spark of energy, lost in the noise of your biology. There is a strange peace in knowing you are porous. You feel solid. You feel like a barrier. But to the universe, you are transparent. You are a window. The cosmos is streaming through you right now, carrying information from the heart of the sun. And you are none the wiser. Let the ghosts pass. You cannot stop them anyway. But while the neutrinos are ignoring you, there is something else in the room that is paying very close attention to the geometry of space. Let's talk about the Casimir effect. This is a phenomenon that proves that nothing pushes back. Imagine we have 2 metal plates, perfect mirrors. We place them in a vacuum, no air, no dust, just empty space. We bring the plates very, very close together, micrometers apart. According to classical physics, there is nothing between them and nothing outside them. They should just hang there, but they don't. They are pushed together. A mysterious force shoves them towards each other. Why? Because of the waves in the vacuum. Remember the quantum foam, the boiling sea of virtual particles and waves. Those waves come in all sizes. Big wavelengths, small wavelengths. Outside the plates, in the open space, all sizes of waves can exist. Big rolling swells and tiny ripples. But inside the narrow gap between the plates, the big waves don't fit. They are excluded. Only the small, short waves can fit in the gap. This means there are fewer waves pushing from the inside than there are pushing from the outside. The pressure of the vacuum is higher on the outside than on the inside. So, the empty space itself crushes the plates together. It is a force from nothing. It is the weight of the missing waves. Think about two ships bobbing on a rough ocean. If they get too close, the water between them gets calm because the big waves can't fit. The rough ocean on the outside pushes the ships together. This is happening on a nanoscale all around you. The vacuum is not passive. It is an active, pressurized ocean. If you bring two things close enough together, the universe will try to seal the gap. It wants to close the distance. It is a subtle reminder that separation requires energy. Intimacy is the default state when the noise is removed. The universe favors the close. Now, let us step away from the forces and look at the strange logic of quantum computing. You might have heard the term, usually followed by stock market buzzwords, but the science of it is a perfect bedtime paradox. It all comes down to the difference between a bit and a qubit. In the computer or phone you are using to listen to this, information is stored in bits. A bit is a switch. It is either 0 or 1, off or on. It is binary. It is decisive. This is the logic of the day. Yes or no, true or false. But a quantum computer uses qubits. And a qubit relies on superposition. A qubit is not 0 or 1. It is a complex mixture of 0 and 1 at the same time. It is a sphere of possibilities. Imagine a coin. A classical bit is a coin that has landed. It is heads or it is tails. A qubit is a coin that is spinning on the table. It is a blur of heads and tails. It contains more information because it is in motion. If you try to solve a maze with a classical computer, it has to try every path one by one. Left turn, dead end, go back. Right turn, dead end, go back. It takes time. A quantum computer, using the logic of the qubit, can try every single path of the maze simultaneously. It floods the maze like water. It finds the exit instantly because it was never restricted to being in one place at one time. It is the power of indecision. We are taught that indecision is bad. We are taught to make up our minds. Pick a major, pick a career, pick a side. But the quantum world tells us that indecision is a superpower. Keeping your options open, remaining in a state of superposition, allows you to explore all possibilities at once. The moment you choose, the moment you collapse the wave function, you lose that power. You become a classical bit. You become a single frozen outcome. So, as you lie in the dark, do not worry about the decisions you haven't made yet. Do not worry about the uncertainty of tomorrow. You are just being a qubit. You are processing all the paths. You are spinning on the table. And as long as you are spinning, you are infinite. There is plenty of time to land later. For now, just spin. Let's drift to a concept that challenges the flow of time itself. We touched on the arrow of time, but there is a new form of matter that breaks the symmetry of the clock. They are called time crystals. It sounds like something from a fantasy novel, a gem you would put in a wizard's staff. But it is a real phase of matter, created in a lab. Normal crystals, like the salt in your kitchen or the diamond in a ring, have a pattern that repeats in space. Atom here, atom there, atom here. A repeating grid. They break spatial translation symmetry. A time crystal is different. It has a pattern that repeats in time. If you poke a normal system, it usually settles down. It reaches equilibrium. It stops moving. But if you poke a time crystal, it reacts in a repeating loop that never loses energy. It ticks, tick, 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 forever. Without any energy source, it is a system that prevents itself from ever reaching thermal equilibrium. It refuses to settle. It refuses to die. It is stuck in a loop of time, flipping back and forth between states, eternally keeping the beat. It breaks time translation symmetry. It says that this moment is not the same as the next moment, but the moment after that will be exactly the same. It is a heartbeat of matter. Imagine a jelly that, when you tap it, jiggles forever, never stopping, never slowing down. That is the essence of a time crystal. It defies the laws of thermodynamics that say everything must eventually run down and stop. It cheats the heat death of the universe. It is a reminder that the rules we think are absolute, like the rule that you must get tired, or the rule that things must stop, have loopholes. The universe is full of loopholes, and maybe, just maybe, consciousness is a bit like a time crystal, a pattern that repeats, a rhythm that sustains itself against the entropy of the world. You close your eyes, you lose yourself, and then you wake up and the pattern resumes. You are a repeating event in the fabric of space-time. Now, let us zoom out from the crystals and look at the field that fills the entire universe. The invisible molasses. The Higgs field. For a long time, physicists couldn't figure out why things have mass. Why does an electron weigh something? Why is a proton heavy? Why isn't everything just flying around at the speed of light, weightless and free? If there was no mass, there would be no atoms, no stars, no you, just light zipping through the void. In the 1960s, Peter Higgs and others proposed a solution. They suggested that the entire universe is filled with an invisible field. Think of it like a cosmic ocean of syrup, or a room filled with heavy, thick snow. When a particle moves through this field, it interacts with it. The field drags on it. It clings to it. This drag is what we call mass. Some particles, like photons, slice through the field without touching it. They don't interact. So they have no mass. They fly at the speed of light. Other particles, like electrons and quarks, get bogged down. They have to wade through the syrup. They get heavy. They slow down. You are heavy because you are interacting with the Higgs field. Your body is pushing against this invisible ocean, and the ocean is pushing back. If the Higgs field suddenly vanished, your mass would disappear. Your atoms would disintegrate. You would explode into a burst of light and radiation moving at maximum velocity. So, the heaviness you feel in your limbs right now, that pleasant, sinking feeling into the mattress, is not just gravity. It is the result of your fundamental particles wading through the cosmic molasses. You are anchored to reality by this field. It is the glue of existence. It is called the God particle in the media, which scientists hate. They prefer to call it the Higgs boson, but the name captures the magnitude of it. It is the particle that gives substance to the universe. Without it, everything is just a ghost. With it, we have weight, we have consequence, we have a place to rest. Feel that weight now. Feel the Higgs field doing its work. It is giving you presence. It is telling the universe, this object is here. It matters. It has substance. Let the field hold you. You don't have to hold yourself up. The physics is doing it for you. We have talked about the very small and the very cold and the very heavy. But what about the very dark? We cannot talk about the weirdness of the universe without acknowledging that we only know about 5% of it. Look at the room around you in your mind's eye. The walls, the air, the dust. That is baryonic matter, normal stuff. Protons, neutrons, electrons. That accounts for 5% of the energy budget of the universe. The other 95%, we have no idea what it is. 27% is dark matter. Dark matter is the ghost gravity. When we look at galaxies, we see them spinning, but they are spinning too fast. Based on the visible stars, there isn't enough gravity to hold them together. They should be flinging themselves apart. Stars should be ejected into the void, but the galaxies hold together. Something invisible is gripping them. A massive, unseen halo of stuff that has gravity but does not interact with light. It passes right through you, just like the neutrinos. But it is heavy. It is likely that right now, dark matter is flowing through your bedroom. It is clumping in the corner. It is drifting through the walls, an invisible scaffolding that holds the shape of the Milky Way together. You are sleeping inside a galaxy that is mostly made of stuff you cannot see and will never touch. And then there is the remaining 68%, dark energy. If dark matter is the glue that holds things together, dark energy is the wind that blows them apart. It is the energy of empty space, and it is pushing. It is accelerating the expansion of the universe. It is a force of anti-gravity, a cosmic repulsion. So you are caught in a tug of war. The dark matter is trying to pull the universe into a ball. The dark energy is trying to tear the universe into shreds, and you are in the middle, made of the rare, precious 5% of normal matter, just trying to get a good night's sleep. It puts your problems into perspective. The universe is fighting a civil war over the geometry of space-time, and you are worried about whether you locked the front door. The door is locked. The protons are holding. The Higgs field is sticky. You are safe. But let's return to something a little more intimate. Something that happens inside your own skull. The concept of the quantum brain. For decades, neuroscientists treated the brain like a wet computer. Neurons are wires. Synapses are switches. Electrical signals travel down the wire, flip the switch, and create a thought. Classical physics. But recently, the sleepless scientist has been reading papers that suggest the brain might be a quantum computer. There are structures inside your neurons called microtubules. They are tiny tube-like skeletons that give the cell its shape. Some physicists, most notably Roger Penrose, have argued that these microtubules are small enough to isolate quantum effects. They suggest that consciousness, the feeling of being you, is not a computation, it is a quantum collapse. They call it orchestrated objective reduction. The idea is that your brain is constantly generating a superposition of possibilities, a cloud of maybe thoughts. And then, at a specific moment, the wave function collapses and a single conscious moment is born. I am. Then the wave builds up again and collapses again. I am. Consciousness is not a continuous stream. It is a series of quantum beats, a strobe light of existence. We think we are fluid, but we might be discrete. We are flickering into existence 40 times a second. If this is true, then sleep is just a longer pause between the beats. It is a moment where the orchestra stops playing and the wave function is allowed to drift without collapsing. When you dream, maybe you are exploring the uncollapsed wave. You are surfing the superposition without the harsh reality of the reduction. It explains why dreams are so weird. Why 1 minute you are in your childhood home and the next you are on a boat. In the quantum view, both those locations were in the superposition. You just visited both without filtering them. So, do not be afraid of the drift. You are just letting your microtubules rest. You are letting the quantum soup simmer without trying to ladle it into a bowl. Let the strobe light slow down. Let the flickers get further apart. The gap between the I and the am is growing. I am. And in that gap, there is peace. But we are not done yet. There is one more paradox we need to inspect before we truly shut down the core. The paradox of the Boltzmann brain. Ludwig Boltzmann was a pioneer of thermodynamics. He understood entropy, the tendency of the universe to get messy. He knew that it is very unlikely for atoms to randomly arrange themselves into something organized. It is much more likely for them to be a chaotic gas. But here we are. We are organized. The universe has stars and planets and people. This is a very low entropy state. It is statistically incredibly unlikely. So Boltzmann proposed a disturbing idea. He said that in an infinite universe that lasts for an infinite amount of time, particles will randomly collide. Eventually, just by pure chance, they will bump into each other in a way that forms a structure. Usually, it will just be a rock or a dust bunny. But if you wait long enough, an eternity, eventually, the random fluctuations of the vacuum will spontaneously assemble a human brain, complete with memories, complete with the feeling of existing. This brain would exist for just a second, floating in the void, hallucinating a reality, and then dissolve back into the chaos. This is a Boltzmann brain. The paradox is this: it is statistically trillions of times more likely for a single brain to randomly pop into existence than for an entire universe to be created with billions of stars and billions of years of evolution. So, the math asks a rude question. Are you a real person with a history, living in a real universe? Or are you a Boltzmann brain that just materialized in the void a split second ago, complete with false memories of a life you never lived, listening to a hallucinated YouTube video about quantum mechanics? You cannot prove you aren't. Your memory of breakfast this morning? Implanted by the random collision of particles. Your memory of childhood? Just a pattern of neurons that formed by accident. It is the ultimate solipsism. But before you panic, Remember the sleepless scientist motto: if you can't change it, don't worry about it. If you are a Boltzmann brain, you are a very detailed one. The hallucination is consistent. The bed feels soft. The voice is deep. The concepts are interesting. You might as well enjoy the ride. And if you are a real person, evolved from stardust over billions of years, then you are a triumph of order over chaos. You are a statistical miracle. You are a fortress of structure in a universe that wants to be soup. Either way, you exist. And either way, you are tired. The Boltzmann brain needs to power down just as much as the biological one. Let's step back from the edge of existential dread and look at something beautiful: the geometry of spin. We mentioned earlier that electrons have spin, up or down, but we didn't explain how weird that actually is. If you take a ball and rotate it 360 degrees, one full circle, it looks the same. It is back to where it started. If you take a playing card, the Queen of Hearts, and rotate it 360 degrees, she is upright again. But an electron has spin 1/2. This means that if you rotate an electron 360 degrees, it is not back to where it started. It has changed. It is actually facing the opposite way. Mathematically speaking, you have to rotate an electron 720 degrees, 2 full circles, to get it back to its original state. Think about that. A particle that has to spin around twice to see the same view once. It implies that the electron sees a bigger universe than we do. It sees a layer of geometry that we are blind to. It suggests that space itself is twisted in a way that requires a double loop to traverse. It is like walking around your house. You walk around the block once, and you arrive at your front door, but the house is upside down. You have to walk around the block a second time to get the house right side up. That is the world the electron lives in, a Mobius strip of reality. It is dizzying, but it is also a sign that there is more room than we think. We feel boxed in by our 3 dimensions: up, down, left, right, forward, back. But the particles know secret directions. They know the shortcuts. So when you feel trapped by stress, trapped by the ceiling, trapped by the dark, remember the electron. Remember that a full circle is not the end. There is a second loop. There is a hidden path that brings you back to wholeness. You just have to keep spinning. The lab is getting colder now. The liquid helium is creeping up the beaker. The time crystals are ticking. The neutrinos are streaming. We are reaching the limit of what the conscious mind can hold. The paradoxes are piling up like unread books on a nightstand. The cat is alive and dead. The particle is here and there. The vacuum is empty and full. The time is flowing and frozen. You are real and a hallucination. It is too much. The logic circuits are overheating. And that is good. That is the point. We overload the analysis engine so that it is forced to shut down. We feed the brain so much impossible data that it finally throws up its hands and says, "Fine, I quit. Let's go to sleep." Surrender to the confusion. Surrender to the fuzziness. You do not need to understand the universe to live in it. You do not need to know how the engine works to drive the car. You are the passenger tonight. The laws of physics are driving. The Pauli exclusion principle is holding you up. The Higgs field is holding you down. The thermal vibrations are keeping you warm. The quantum tunneling is keeping your chemistry flowing. You are being taken care of by the machinery of the cosmos. It is a silent, automated, uncaring, yet perfectly reliable machine. It doesn't know your name, but it knows exactly how to bind your atoms together. Trust it. Feel the darkness pressing against your eyelids. That is not just absence of light. That is the universe waiting for you to join the superposition. When you sleep, you become a wave again. You spread out. You touch the edges of the possible. So let the focus soften. Let the words I am saying lose their meaning. Let them become just sound, just vibration, just waves in the air, phonons, sound particles, hitting the drum of your ear, turning into electrical signals, fading into the neural web, fading. The cooling fan is the only thing left. The white noise of the server rack, a steady, constant, flat line of sound. It masks the ticking of the time crystal. It masks the hum of the vacuum. It is the lullaby of the laboratory. We are just atoms studying atoms. We are just the universe trying to understand itself and getting tired in the process. There is no shame in the fatigue. Even the stars run out of fuel. Even the black holes evaporate. Even the protons might eventually decay. Eons from now, rest is the destiny of all things. Entropy wins in the end. The disorder increases. The energy spreads out. The heat cools. And that is okay. Because entropy is also relaxation. Order is stress. Maintaining a neat room takes energy. Maintaining a focused mind takes energy. Entropy is letting go. It is letting the room get messy. It is letting the thoughts scatter. Embrace the entropy. Let your mind become a high entropy state. Disordered, random, calm, drifting. You are safe in the midnight lab. The sleepless scientist will keep watch. I will watch the dials. I will monitor the wave functions. I will keep an eye on the cat. You can stop observing now. You can stop collapsing the world. Let it be a blur. Let it be quiet. But the quiet is deceptive. In the midnight lab, silence is not a lack of activity. It is simply a lack of witnesses. While your ears detect nothing but the fan, the universe is busy balancing its books in a way that is profoundly uncomfortable if you think about it too hard. So, let us think about it too hard. Lift your hand in the darkness. You cannot see it, but you know it is there. You have a left hand and you have a right hand. They look identical. If you hold them up to a mirror, the left becomes the right and the right becomes the left. For centuries, physicists believed the universe treated left and right exactly the same. They believed in parity conservation. They thought that if you built a machine that was a mirror image of our world, it would work exactly the same way. It was a comforting thought. It meant the universe was balanced. It meant nature didn't play favorites. But in 1956, the universe revealed that it is, in fact, crooked. A physicist named Chien-Shiung Wu, known as the First Lady of Physics, set up an experiment with cobalt-60 atoms. She cooled them down, much like we have cooled down our imagination tonight to near absolute zero, so the thermal jitter wouldn't mess up the data. She applied a magnetic field to line up the nuclei like little spinning tops. If the universe was symmetrical, the electrons shooting out of these decaying atoms should have gone up and down in equal numbers, but they didn't. They overwhelmingly shot out in one direction. It was a shock to the system. It meant that on a fundamental level, the weak nuclear force, the force responsible for the radiation that powers the sun, is left-handed. The universe has a preference. It is asymmetrical. If you were to communicate with an alien civilization on a distant planet, and you described to them exactly how to build a car, or a sandwich, or a clock, they could build it perfectly. But without seeing you, they would never know if they built a left-handed clock or a right-handed clock. Until Madame Wu's experiment. Now we can tell them to look at the decay of cobalt-60. This shattered the idea of a perfect mirror image perfection. It suggests that reality itself has a twist, a quirk, a built-in bias. So as you lie there, consider that you are living in a left-handed universe. You are part of a reality that is fundamentally slightly lopsided. And perhaps that is why you toss and turn. You are trying to find the comfortable groove in a mattress that was designed by a crooked architect. But the mirror image problem gets worse. It is not just about left and right. It is about the substance of creation itself. Let us talk about the evil twin of matter, antimatter. In 1928, Paul Dirac was playing with equations. He was trying to combine quantum mechanics with Einstein's special relativity. He came up with an equation that worked beautifully, but it had a strange quirk. It allowed for particles with negative energy. Most people would have thrown the equation out. Negative energy sounds like a bank account error. It shouldn't exist. But Dirac was bold. He suggested that for every particle of matter, there is a corresponding particle of antimatter. Same mass, but opposite electric charge. 4 years later, he was proven right. We found the positron, the anti-electron. Here is the terrifying part. When matter meets antimatter, they do not bounce off each other. They do not bond. They annihilate. They completely destroy each other, converting 100% of their mass into pure energy, pure gamma radiation. It is the most violent reaction known to physics. A paperclip of antimatter reacting with a paperclip of matter would release the energy of a small nuclear bomb. Now, look at the room around you. The bed, the walls, the air. It is all made of matter. Where is the antimatter? According to the Big Bang Theory, the universe should have been created with equal amounts of matter and antimatter. 50-50. Perfect balance. But if that had happened, all the matter and all the antimatter would have mixed together in the first fraction of a second. They would have annihilated. The universe would have ended before it began. It would be nothing but a bath of pure light. No stars, no atoms, no you. But that didn't happen. Somehow, in those first chaotic moments, there was a slight imbalance. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. 1,000,000,000 pairs annihilated. Boom. They turned into the background radiation we can still detect today. But that one single survivor, that one lonely particle of matter left over, that is what you are made of. You are the leftover dust. You are the rounding error. You are the cosmic debris that remained after the Great War of Annihilation. Every star in the sky, every galaxy, every planet, and every cell in your body is made of the tiny fraction of material that failed to find a partner to destroy it. We are the anomaly. The universe is mostly empty space and radiation. Matter is the exception. Existence is a statistical fluke. Does that make you feel small, or does it make you feel lucky? You are the 1 in a billion that made it out of the fire. You are the survivor, and you are still surviving. Right now, there is antimatter in your room. Bananas are rich in potassium. A tiny fraction of that potassium is a radioactive isotope, potassium-40. Every 75 minutes or so, a banana will spit out a positron, an antimatter particle. If you have a fruit bowl in your kitchen, it is a tiny antimatter generator. The positron flies out, hits an electron in the air molecules, and annihilates in a tiny invisible flash of gamma rays. It is happening constantly. A microscopic war of opposites fought in the fruit bowl while you sleep. But do not worry. The amount is small. You are not going to explode. The universe has biased the game in your favor. Matter won. The dangerous twins have been banished to the edges of the galaxy or the centers of high-energy experiments. But what if the ground beneath your feet was not as stable as you thought? I do not mean the floorboards. I mean the laws of physics themselves. We have spoken about the vacuum state, the lowest energy state. A ball rolling down a hill will stop at the bottom. That is the vacuum, the ground floor. But what if we are not at the bottom of the hill? What if we are resting on a ledge? This is the theory of the false vacuum. Imagine a hiker standing on a ledge halfway down a mountain. He looks down and sees the valley floor far below. He is stable on the ledge, but he is not at the lowest point. Physicists suspect that the Higgs field, the molasses that gives you mass, might be stuck on a ledge. It might be in a metastable state. It looks stable. It has been stable for 13.8 billion years, but it is not the true bottom. There is a theory that at any moment through a random quantum tunneling event, a tiny point of the universe could realize, hey, I can go lower. It would tunnel through the ledge and drop to the true vacuum. If this happens, it releases energy. A bubble of true vacuum would form. Inside this bubble, the laws of physics would be different. The constants of nature would change. Chemistry would not work. Atoms would not hold together, and this bubble would expand. It would grow at the speed of light. Because it moves at the speed of light, you would never see it coming. Information cannot travel faster than light. So, the warning signal would arrive at the exact same moment as the destruction. One moment, you are lying in bed, listening to the hum of the fan. The next moment, you are simply deleted. Your atoms would fall apart. The forces holding you together would rewrite themselves into something unrecognizable. It would be the ultimate painless instant end. A cosmic off switch. It sounds terrifying. A bubble of doom sweeping through the galaxy, erasing history. But in the context of sleep, it is strangely calming. It takes the responsibility out of your hands. There is absolutely nothing you can do about vacuum decay. You cannot prepare for it. You cannot dodge it. You cannot insure against it. It is a sword of Damocles that hangs over the entire universe. Not just you. And if the universe can sleep under that threat, so can you. The probability is infinitesimally low. It might not happen for googles of years, or it might have happened a billion light years away 5 minutes ago. And the bubble is rushing towards us right now. But let's be sardonic about it. If the laws of physics are going to be rewritten, maybe the new ones will be better. Maybe in the new universe, coffee doesn't get cold and printer ink is free. Until then, we live on the ledge. We build our houses on the cliffside of energy potentials, and we enjoy the view. And what a view it is. Let's look deeper into the weird zoo of particles. We have talked about the common ones, the protons, electrons, neutrons, the vanilla ice cream of reality. But there are other flavors, quarks. Protons and neutrons are made of quarks, specifically up quarks and down quarks. A proton is 2 ups and a down. A neutron is 2 downs and an up. Everything you have ever touched is made of these 2 types. But there are 4 other types of quarks. Charm, strange, top, bottom. Physicists are terrible at naming things, but they are great at finding nightmares. Let's talk about strange quarks. They are heavier than the regular ones. They usually decay very quickly. But there is a hypothesis called the strange matter hypothesis. It suggests that inside the crushing pressure of a neutron star, a dead star that is incredibly dense, the protons and neutrons might break down. The quarks might spill out and mix together. Under this pressure, some of the quarks might turn into strange quarks. The result is strange matter, a soup of up, down, and strange quarks. And here is the kicker. Strange matter might be the true ground state of matter. It might be more stable than the atoms you are made of. This leads to the concept of a strangelet, a tiny nugget of strange matter. If a strangelet were to escape a neutron star and drift through space, perhaps carried by that dark matter wind we talked about, and it were to hit Earth, it would not just punch a hole. Because strange matter is more stable, any normal matter that touches it would want to become strange matter. It would lower its energy by converting. So, the strangelet would touch an atom of Earth. That atom would dissolve and turn into strange matter. This releases energy and heat and touches the next atom. It would start a chain reaction, a contagion of physics. The strangelet would fall to the center of the Earth, eating everything in its path, converting the rock and the iron into strange sludge. Eventually, the entire Earth would be converted into a hot, dense ball of strange matter, the size of a baseball stadium, but with the mass of the entire planet. Congratulations, the sleepless scientist whispers. You are now a quark nugget. But again, the probabilities are on your side. We have been hit by cosmic rays for billions of years, and we are still here. We are still made of boring, unstable, up and down quarks. It seems the universe prefers variety over stability. It prefers the complex, fragile dance of atoms to the dense, boring sludge of strange matter. So, appreciate your fragility, Your body is a delicate, unstable arrangement of chemistry that is fighting against the urge to collapse into a lower energy state. You are fighting the gravity, the vacuum decay, and the strangelets. And you are winning. Every breath you take is a victory lap. Inhale, exhale. That was a victory. Now, let us shift gears. We have looked at the things that could destroy us. Let us look at the things that might explain why we are here at all. The Goldilocks enigma. The universe seems suspiciously perfect for life. If the force of gravity were slightly stronger, stars would burn through their fuel in 1,000,000 years. Too fast for evolution, we wouldn't be here. If gravity were slightly weaker, stars would never ignite. No suns, no heat, we wouldn't be here. If the strong nuclear force were slightly different, carbon wouldn't form. No biology, we wouldn't be here. If the expansion rate of the universe were slightly faster, galaxies wouldn't form. If it were slower, the universe would have collapsed back into a big crunch eons ago. It feels like someone adjusted the dials on the mixing board of reality to get the sound exactly right. This is the fine-tuning problem. Why are the constants of nature just right? There are two main answers. One is religious, which is not our department. The other is statistical, which is very much our department. It is the anthropic principle. It states, we observe these conditions because if they were any different, we wouldn't be here to observe them. It is a tautology. It is like a puddle of water waking up and saying, wow, this hole in the ground fits me perfectly. It must have been made just for me. No, the puddle fits the hole because the water flows to fill the shape. In the context of the multiverse, the library of many worlds we visited earlier, it makes sense. Imagine there are infinite universes. In most of them, gravity is too strong. Crunch. Dead universe. In others, the weak force is too weak. No stars? Dark universe. There are trillions of dead, empty, broken universes filling the shelves of the library. But in a few of them, rare, precious jewels, the numbers align. The stars ignite. Carbon forms. Complexity arises. And eventually, a sleepless primate evolves to wonder about it. You are here because you couldn't be anywhere else. You are the winner of a cosmic lottery you didn't know you entered. But this leads to a stranger thought. A thought that might keep you awake or might make you immortal. Quantum immortality. We talked about the many worlds theory. Every time a quantum event happens, the universe splits. Now, imagine a version of Schrödinger's cat experiment, but with a human observer inside the box. Let's call him Bob. Bob gets in the box. The probability of the poison releasing is 50-50. In 50% of the universes, Bob dies. In 50% of the universes, Bob lives. From the outside perspective, we see Bob die half the time. But from Bob's perspective, Bob cannot experience a universe where he is dead. Consciousness requires existence. So, from Bob's point of view, he always wakes up in the branch where the poison didn't fire. He runs the experiment again. 50-50. Again, half the versions of Bob die. But the consciousness of Bob, the I am, can only continue in the timeline where he survives. So to Bob, It seems miraculous. The gun jams. The poison fails. The hammer breaks over and over again. In the multiverse, there is always a branch, no matter how thin, where you survive. If this logic holds, and it is a controversial if, it suggests that you might never experience your own death. You might get old. You might get sick. But in the sliver of probability where your consciousness can persist, it does. You are surfing the edge of the wave of survival. It is a lonely kind of immortality. Everyone else around you might see you pass away in their timelines. But in your timeline, you just keep going. The sleepless scientist keeps broadcasting. The fan keeps humming. It suggests that consciousness is a persistent illusion that refuses to leave the stage. So, why worry about the end? According to the math of the many worlds, you might just be the one observer who never blinks. But let's step back from the edge of eternity. That is too much pressure for a Tuesday night. Let's look at something that breaks the rules of cause and effect. We assume that the past causes the future. You knock a glass over, it breaks. The knock caused the break. But in the quantum world, the arrow can point both ways. We talked about the delayed choice eraser, but let's scale it up. John Wheeler, a giant of physics, proposed a cosmic delayed choice. Imagine a quasar, a super bright galaxy, billions of light years away. Its light travels towards Earth. Between Earth and the quasar is a massive galaxy. Its gravity acts like a lens, bending the light. The light can go around the left side of the galaxy or the right side. Billions of years ago, the photons left the quasar. They traveled through the void. They passed the galaxy. Now, today, on Earth, an astronomer points a telescope at the quasar. He can choose to measure which path the light took, left or right, or he can choose to measure the interference pattern, wave behavior. Just like in the double-slit experiment, his choice determines whether the light acted like a particle or a wave. But here is the twist. The light passed the galaxy billions of years ago. The choice the astronomer makes tonight determines the path the photon took billions of years ago. Did the photon go left? Did it go right? Did it go both ways? The answer depends on what you decide to do with your telescope right now. This suggests that our actions in the present are reaching back through deep time and knitting the fabric of the past. We are not just passive observers of history. We are, in a quantum sense, the authors of it. The stars you see out your window, your observation of them is finalizing their journey. You are collapsing their wave functions after a million-year voyage. You are the destination they have been waiting for. Without your eye to catch the photon, its history remains a blur. With your eye, it becomes a story. So, look at the night sky, or imagine it. You are completing the universe. You are tying up the loose ends of light that have been unraveling since the dawn of time. It is a heavy responsibility, but also a beautiful one. You are the witness that makes the universe real. But what if the particles themselves don't want to be real? What if they want to be fast? Faster than light. We have all heard the speed limit. 299,792,458 meters per second. The speed of light. Nothing can go faster. But the equations of relativity have a loophole. They say you cannot accelerate to the speed of light you would need infinite energy. But what if a particle was born faster than light? What if it never had to accelerate because that was its starting speed? These hypothetical particles are called tachyons. To a tachyon, the speed of light is the slow limit. It can never slow down to light speed. It requires infinite energy to slow down. So it zooms through the universe, always faster than light. And because it moves faster than light, it moves backwards in time. If you could build a telephone using tachyons, you could call yourself 5 minutes ago. You could warn yourself not to drink that second cup of coffee. But then, if you didn't drink the coffee, you wouldn't have called yourself. Paradox. Tachyons create causal loops that give physicists migraines. Most scientists think they don't exist. They are too messy, but the math allows them. Imagine a universe filled with invisible particles rushing backwards through time, carrying messages from a future that hasn't happened yet, trying to rewrite a past that is already fading. Maybe that is what déjà vu is, a tachyon hitting your brain, a glitch in the temporal processing, a memory of something that is about to happen. Or maybe it is just a misfiring neuron. But the tachyon version is more poetic. For a sleepless night, the laboratory is full now. We have filled it with mirrors and antimatter bananas and bubbles of doom and backwards flying time particles. It is a cluttered room, but look at the dust motes dancing in the light of the server LEDs. Brownian motion. In 1827, a botanist named Robert Brown looked at pollen grains in water. They were jittering, dancing. He didn't know why. He thought they might be alive. It took Einstein again to explain it. The pollen was being hit by invisible water molecules. The visible was being moved by the invisible. That is the theme of our night. You are the pollen grain. The world you see, the job, the bills, the traffic is the pollen. But the reason it moves, the reason it jitters, is the invisible sea of quantum mechanics underneath. You are being buffeted by forces you cannot see. And just like the pollen grain, you don't have to steer. You don't have to understand the hydrodynamics of the water molecules. You just have to float. The jitter is natural. The shaking is part of the system. If you feel anxious, if you feel the vibration of the world, know that it is just the thermal noise of the universe. It is not a malfunction. It is a feature. Even the black holes shiver. Even the vacuum boils. Stillness is the only unnatural state, and yet we seek it. We crave the zero. We want to be the superfluid that flows without friction. We want to be the Bose-Einstein condensate that sleeps in a single pile. We are fighting our own biology, which is warm and messy and loud. But the fight is what makes us interesting. If we were perfectly still, we would be frozen. If we were perfectly symmetrical, we would be boring. If we were perfectly stable, we wouldn't exist. We are the beautiful, asymmetrical, unstable, left-handed, oscillating errors of a universe that loves to experiment. And the experiment is currently in sleep mode. Or it should be. The fan is still spinning. The bearings are frictionless enough to keep it quiet, but not frictionless enough to spin forever. It needs power. You need power. Recharging is a quantum process too. Your mitochondria are moving electrons down a chain, pumping protons across a membrane, creating the chemical battery packets, ATP, that will power you tomorrow. It is a microscopic hydroelectric dam inside your cells. While you lie there doing nothing, your body is generating kilowatts of potential. You are a power plant in standby mode, so do not feel guilty for the rest. You are not inactive. You are refining fuel. You are resetting the qubits. You are preparing for the next collapse of the wave function. Tomorrow, you will open your eyes and the universe will snap back into focus. The blurry map will sharpen. The cat will be alive. The coffee will be hot, but for now, keep the map blurry. Keep the cat in the box. Let the paradoxes protect you. Logic is a daytime tool. It is a hammer for building things in the sun. But at night, you don't need a hammer. You need a blanket. And quantum mechanics, with its fuzziness and its uncertainty, is the ultimate blanket. It covers everything. It softens the edges of the sharp reality. It tells you that exactness is an illusion. So, wrap yourself in the uncertainty. Pull the probability cloud up to your chin. Sink into the foam. The sleepless scientist is checking the final monitors. The tachyon detectors are silent. The antimatter containment is holding. The false vacuum is stable. The experiment is concluding. The data has been collected. The conclusion is simple. The universe is weird, but it is waiting for you to wake up to keep the story going. But it can wait a few more hours. The stars aren't going anywhere. The protons have a half-life of 10 to the power of 34 years. They will be there when you wake up. There is no rush. Time is relative. Make your night last 1 billion years.